let's say you're some type of traffic engineer, and what you're trying to figure out is how many cars pass by a certain point on a street at any given point in time, and you want to figure out the probabilities that 100 cars pass or 5 cars pass in a given hour. So a good place to start is just to define a random variable that essentially represents what you care about. So let's say the number of cars that pass in some amount of time. Let's say in an hour. In an hour. And your goal is to figure out the probability distribution of this random variable. And then once you know the probability distribution, then you can figure out, what's the probability that 100 cars pass in an hour, or the probability that no cars pass in an hour, and you'd be unstoppable. So, and just a little aside, just to move forward with this video, there's 2 assumptions we need to make, because we're going to study the Poisson distribution. In order to study it, there's 2 assumptions we have to make. That any hour at this point on the street is no different than any other hour. And we know that's probably false. During rush hour in a real situation, you probably would have more cars than in another rush hour. And if we wanted to be more realistic, maybe we do it in a day, right? Because in a day, any period of time, actually no, I shouldn't do a day. We have to assume that every hour is completely just like any other hour, and actually even within the hour, there's really no differentiation from one second to the other in terms of the probabilities that a car arrives. So that's a little bit of a simplifying assumption that might not truly apply to traffic, but I think we can make that assumption. And then the other assumption we need to make is that if a bunch of cars pass in 1 hour, that doesn't mean that fewer cars will pass in the next. That in no way does the number of cars that pass in one period affect or correlate or somehow influence the number of cars that pass in the next. That they're really independent. Given that, we can then at least try using the skills we have to model out some type of a distribution. The first thing you do, and I'd recommend doing this for any distribution, is that maybe we can estimate the mean. Let's sit out on that curb and measure what this variable is over a bunch of hours and then average it up, and that's going to be a pretty good estimator for the actual mean of our population, or since it's a random variable, the expected value of this random variable. Let's say you do that, and you get your best estimate of the expected value of this random variable is, I'll use the letter lambda. So this could be 9 cars per hour. You sat out there, or, it could be 9.3 cars per hour. You sat out there over hundreds of hours, and you just counted the number of cars each hour, and you averaged them all up, and you said, on average, there are 9.3 cars per hour, and you feel that's a pretty good estimate. So that's what you have there. And let's see what we could do. We know the binomial, the distribution, right? The binomial distribution tells us that the expected value of a random variable is equal to the number of trials that random variable is kind of composed of, right? Before, in the previous videos, we were counting the number of heads in a coin toss. So this would be the number of coin tosses times the probability of success over each toss, right? This was what we did with the binomial distribution. So maybe we can model our traffic situation something similar. This is the number of cars that pass in an hour, right? So maybe we could say, lambda cars per hour is equal to, I don't know, let's make each experiment or each toss of the coin equal to whether a car passes in a given minute. So there's 60 minutes per hour, and then there would be 60 trials, and then the probability that we have success in each of those trials, if we model this as a binomial distribution, would be lambda over 60 cars per minute. And this would be a probability. This would be n, and this would be the probability. If we said that this is a binomial distribution, and this probably wouldn't be that bad of an approximation. If you actually then said, oh, this is a binomial distribution, so the probability that our random variable equals some given value k, the probability that exactly 3 cars pass in a given hour, it would then be equal to n, so n would be 60, choose k, and 3 cars, times the probability of success, so the probability that a car passes in any minute, so it would be lambda over 60 to the number of successes we need, so to the kth power, times the probability of no success, or that no cars pass, to the n minus k, right? If we have k successes, we have to have 60 minus k failures. There are 60 minus k minutes where no car passed. And you know, this actually wouldn't be that bad of an approximation where you have 60 intervals and you say this is a binomial distribution, and you probably get reasonable results. But there's a core issue here. In this model, where we model it as a binomial distribution, what happens if more than one car passes in an hour? Right? Or more than one car passes in a minute. The way we have it right now, we call it a success if one car passes in a minute. And if you're kind of counting, it counts as one success, even if 5 cars pass in that minute. And so you say, oh, okay, Sal, I know the solution there. I just have to get more granular. Instead of dividing it into minutes, why don't I divide it into seconds? So the probability that I have k successes, I'll do, instead of 60 intervals, I'll do 3,600 intervals. And so the probability of k successful seconds, so a second where a car is passing at that moment, out of 3,600 possible seconds, so that's 3,600 choose k, times the probability that a car passes in any given second. Well, that's the probability, that's the expected number of cars in an hour divided by number of seconds in an hour. And we're going to have k successes, and then we're going to have, and these are the failures, the probability of a failure, and you're going to have 3,600 minus k failures. And this would be even a better approximation. This actually would not be so bad, but still you have the situation where, you know, 2 cars can come within half a second of each other, and you say, oh, okay, so I see the pattern here. We just have to get more and more granular. We have to just make this number larger and larger and larger, and your intuition is correct. And if you do that, you'll end up getting the Poisson distribution. And this is really interesting because a lot of times people give you the formula for the Poisson distribution and you can kind of just plug in the numbers and use it. But it's neat to know that it really is just the binomial distribution. And the binomial distribution really did come from kind of the common sense of, you know, flipping coins. That's where everything is coming from. But before we kind of prove that this, if we take the limit as, let me change colors. Before we prove that as we take the limit as this number right here, the number of intervals approaches infinity, that this becomes the Poisson distribution, I'm going to make sure we have a couple of mathematical tools in our belt. So the first is something that you're probably reasonably familiar with by now, but I just want to make sure that the limit as x approaches infinity of 1 plus a over x to the x power is equal to e to the a x, is equal to e to the a. And just to prove this to you, let's make a little substitution here. Let's say that n is equal to, let me say 1 over n is equal to a over x, and then what would be x would be equal to na, right? X times 1 is equal to n times a. And so the limit as x approaches infinity, as x approaches infinity, what does a approach? A is, as x approaches infinity, what does n approach? Well, n is x divided by a, right? So n would also approach infinity. So this thing would be the same thing as just making our substitution. The limit as n approaches infinity of 1 plus a over x, I made the substitution as 1 over n. And x is, by this substitution, n times a. And this is going to be the same thing as the limit as n approaches infinity of 1 plus 1 over n to the n, all of that, to the a. And since there's no n out here, we could just take the limit of this and then take that to the a power. So that's going to be equal to the limit as n approaches infinity of 1 plus 1 over n to the nth power, all of that to the a. And this is our definition, or one of the ways to get to e. If you watch the videos on compound interest and all of that, this is how we got to e. And if you try it on your calculator, just try larger and larger n's here, and you'll get e. So this is equal to, this inner part is equal to e. So, and we raise it to the a power, so it's equal to e to the a. So hopefully you're pretty satisfied that this limit is equal to e to the a. And then one other toolkit I want in our belt, and I'll probably actually do the proof in the next video. The other toolkit is to recognize that x factorial, let me do this, x factorial over x minus k factorial is equal to x times x minus 1 times x minus 2 all the way down to times x minus k plus 1. And we've done this a lot of times, but this is the most abstract we've ever written it. I can give you a couple of examples. And there will be exactly, and just so you know, there will be exactly k terms here. 1, 2, 3. So this is the first term, second term, third term, all the way, and this is the kth term. And this is important to our derivation of the Poisson distribution. But just to make this in real numbers, you know, if I had 7 factorial over 7 minus 2 factorial, that's equal to 7 times 6 times 5 times 4 times 3 times 2 times 1 over 2 times, no, sorry, 7 minus 2, this is 5. So it's over 5 times 4 times 3 times 2 times 1. These cancel out, and you just have 7 times 6. And so it's 7, and then the last term is 7 minus 2 plus 1, which is 6. 7 minus 2 plus 1. And you had, in this example, k was 2, and you had exactly 2 terms. So once we know those two things, we're now ready to derive the Poisson distribution, and I'll do that in the next video. See you soon.